these numbers include the whole bus interface. So besides the one-to-one mapping, I consider them quite good. Here we see some device usage. So for this basic block seen on this example, we use about 1% of the FPGA resources. Yeah. And so I'm getting to the to-do. So I have to, what's still to be done is fix the missing stuff, like the extracting of the memory addresses, and fix some corner cases in more, if I'm feeding it more complicated examples. Then to create dedicated optimization paths suitable for hardware implementation. Also, and then what's also on my agenda is to create a more optimized hardware backend, which has not a one-to-one backend, but a more sophisticated backend, which has a more not so demanding resource usage for larger algorithms. Then I'm also looking into fully migratable algorithms. They are partially in the making, and then currently there is no usage of the free CPU power if the control flow is transferred to the hardware. So currently the CPU only waits, and this is of course not so good, but so there should be an operating system or something like that which utilizes the then free CPU power. The goals of this project were an automatic hardware-software co-design flow, completely integrated into the LLVM toolchain. This was realized using intrinsics. These intrinsics were made known to the PowerPC backend, and then a custom VHDL backend has been created, and this whole stuff has been integrated into LLVM and into the Xilinx tool chain. So given the fact that it's a pretty complicated design flow, it's pretty good integrated. Stuff I did not cover in this talk were some optimization passes which handle, for example, constant arrays for the hardware backend. So, and much more efficient hardware paths, which is using a genetic algorithm for multidimensional optimizations. So, if you have some questions on this stuff, we can probably talk about it or write on. So, thanks for listening. Okay, there's some questions.
Yeah, so you create this bytecode for programming the hardware. How long does that actual process take? Is that something that could ever conceivably be done in a JIT, for instance? Okay,
if you think, okay, no, first the question. So the question is, how long does it take to synthesize the hardware, and if it would be possible to create to JIT it, right? Okay, if you take a simple serial device and an interrupt register or counter or something like that, it takes on about 2 minutes to synthesize. So that's a pretty simple hardware. If we're going to much more complex hardware, like stuff you automatically generate out of software, yeah, not in minutes, but more than in hours. So thinking about JITting it is probably not the best idea. Okay.
What's the latency of the migrate begin, migrate end? Because if you want to, I assume it's for performance.
Okay, you have the function call, of course, for this migrate begin instruction, and you have a bus transfer for every parameter which has to be function argument which has to be transferred to the hardware. So we have function call, each bus transfer. You can't say absolute numbers because the bus is not.
I just have you found it to be beneficial? Like, are the workloads for the hardware large enough that the time to describe to the hardware and get results, like to send the commands over there and get results back?
Unfortunately, due to the problems I have with the hardware addresses integration, I have not used big examples because I had to include the hardware addresses by hand. If you're using a bigger example, it's tedious and error prone. So I don't have very good numbers for larger algorithms. So currently I don't know.
Is there any long-term future work you're looking at potentially generating programmable hardware? And then actually generating software to run on that programmable hardware?
It would be nice, but
it's a hard problem.
Yeah, it's quite hard. So it would be. I think it would be quite some heavy lifting and not enough manpower, I would say, for that.
So it looks like you're compiling in physical addresses into the Xilinx program. So are you using, is that a physical address machine? It's not actually virtually addressed? So that you're always going to be putting that data in the same physical address?
Yes, currently it is like that.
So that whole machine is physically addressed, or what?
Yes, we're currently running in a physical addressed machine.
So like the TLB is just straight through?
Yeah, if we're using an operating system, the memory lookup, the lookup of the addresses would be much more complicated, and they would have to be in a way to look up the TLB and stuff like that. But it's complicated as is like that, so probably later on.
You couldn't have a register that you were just writing on the Xilinx where you just gave it an address?
Like an offset kind of.
I extracted the address of the software part, and since we are in real mode, the addresses are one-to-one mapped to the memory addresses, and these are then integrated into the hardware parts. So both parts know about, agree on the software addresses.
But if you mean if the hardware was programmed to have a register, can you not write? So you have to just interrupt the chip. You can't actually write, create a register on the hardware and write to a register on the chip.